Hello, my name is Gerald Coe and I'm going to walk you through a simple project to flash an LED on the IceFun module using the Avalanche processor. Before we start, I'm going to assume that you've already installed the IceStorm toolchain. If you haven't, you should do that now. To install these tools, go to clifford.at/IceStorm. If you'll scroll down, you'll find the instructions for installing the IceStorm tools, NextPNR and USIS, and you'll need these three tools installed. For NextPNR, I would advise that you go to the GitHub repository. If you scroll down, you'll find installation instructions there. The prerequisites are much more comprehensive than they are on the IceStorm website. We're going to need a couple of other programs, the Avalanche assembler and the IceFun programmer tools. So let's install those. First, I'll open up a terminal and copy and paste the GitHub repository. I'm just going to put it in another folder called AVSM. So we'll clone those. Okay, that's downloaded all the files for the assembler. Now if we go into that directory and type make, and that won't take very long to complete. Okay, inside here is created a build folder and AVSM. We're also going to need the IceFun programmer. So again, I'll copy and paste the GitHub repository. CD into that folder. Now for the programmer, we don't have a make file, so we're going to compile it with GCC. So again, I'll copy and paste the command in. It's simply that, and that will build it. If we have a look in there, we have a program, IceFun Prog. We'll need to copy these two programs, IceFun Prog and AVSM, into a folder that's in the search path for your computer. Now if you're not sure where that is, if you can type echo path, you'll get a list of the search locations, and in my case it's in home Jerry bin. Bin is a binary folder. I've created that in my home directory, and on Linux Mint 19.1, which is what we're using here, it will detect the fact that the bin folder is present and automatically add it to the path on your computer. So that's where I've put them. In the bin directory I have AVSM and IceFun Prog. You're also going to need some files that's included with the assembler. And if you go to AVSM, there's a folder here called Avalanche, and that contains the files that you need. So just grab all of those and drop them into your project directory. Okay, these two folders that were created are no longer required. You can keep them if you want to. I'm going to get rid of them. Now we need to create a couple of files. The first is the assembler source code to blink our LED, and the second is the top level Verilog file, which will instantiate our CPU and connect it to the LED. The first thing we're going to do is the assembler source code. So I'm going to create a new document and call it asem.s. Now, as I've said in previous videos, the very first thing you should do in your assembler file is to create three registers. These are the first three registers, register 0, 1 and 2, which must be set to the values 0, 1 and -1. So we'll do that first. Okay, with a little bit of magic, I'll add some comments. Next we set the LED address. This is the port address that we'll be writing to. And again, with a little copy and pasting. So you can gather, I've actually got the code on another screen beside me. We'll set the address to 100 hex. If we have a quick look at the memory map for the CPU, we'll see that we have 256 I/O ports from 100 hex to 1FF, and our LED is going to be at port address 100 hex. This is in the I/O port range. Next thing we need to do is to set up our processors. So we set up our first process, which we've called P1, and within that we must have some code, so we're going to have an endless loop. We just got to jump to a label endless and then end process. Now I'm going to be running the processor at 90 megahertz, so I'm going to define 9 processors so that each process will run at 10 megahertz or 10 MIPS. Okay, we have 9 processors. So if we run our processor at 90 megahertz, each one of these will be running at 10 megahertz. Which is 10 MIPS. Now our first process, we're going to have our Blinky program. So with a little bit of magic, I'll copy and paste that in. And what we're doing here, if we look right in the heart of it, we have a decrement and jump instruction which takes that's a macro which takes 2 native instructions, and that simply decrements a register and jumps to blink 1, which is the same instruction if it's not 0. So this DJNZ instruction is going to be executed 2000 times, and when it's done it decrements delay 2, which is also set to 2000. So effectively this DJNZ instruction is going to be executed 2000 times 2000 4 million times. So as this DJNZ instruction is 2 native instructions, it will actually be executing 8 million instructions. At 10 megahertz, that's 800 milliseconds. So 1.6 seconds cycle time. 800 milliseconds on, 800 milliseconds off. And the actual LED has been written with the contents of counter, which is incremented on each iteration. And as we're going to be using bit 0 for drive the LED, it will simply toggle the LED each time around the loop. The other file that we need is the top level Verilog file. So let's create that. Okay. Now the very first thing that we want to do is include our Avalanche CPU. This is going to be our top level module, and with great originality I'm going to call it top. Now the first thing we're going to be needing in here is an input for our clock. And we're going to be feeding in a 12 megahertz clock. We're also going to be outputting to our LED. And that's a registered output. And we're going to send it to LED 4. And we're also going to have another output. And that's to our column driver. Now that's needed because what we're actually driving is a 4x8 matrix LED display, is 32 LEDs. If we have a quick look at the schematic, we can see that we have 4 rows of 8 LEDs. So if we drive LED 4, we're actually going to be driving the cathode of 4 LEDs, and the column for just this one. So in fact, just L21 will light up. The column drive, this is a PMOS FET, and that transistor will turn on when its gate is at ground level, because that will turn on, and then this will be at 3.3, and that will light up the LED. So LED 4 is going to be the drive that will flash the LED. Alcol 3 will be permanently low, just to light up that one LED. Now you're probably wondering where these names are coming from. And if we look up our pin configuration file, we can see here we've predefined a lot of names to correspond with pins on the FPGA. And LED 4 actually goes to pin A7 on the LED, but these are all predefined for you and you don't need to worry about those. But that is the origin of those names. The next thing we need to do is instantiate a PLL core. We have a 12 megahertz clock coming in, and what we really want to drive the CPU with is a 90 megahertz clock. So we're going to instantiate a PLL. Now, I'm not going to go through this in detail. I'm going to copy and paste this in and show you what it is. Okay. Now, this instantiates the PLL, and you can set this to whatever frequency you need. In this case, it's set to 90 megahertz. If you want to change these values, you can change them. And the easiest way is to use IcePLL. That is a program which is part of the IceStorm toolchain. And I believe this defaults to a 12 megahertz input and I think a 60 megahertz output, and it does. And that gives you the figures for div R, div F and div Q that you can put into here to set the frequency to whatever you want. So in our case, we're going to be wanting a 90 megahertz output. I think it's -O. There we go. 90 megahertz requested and 90 megahertz achieved. And the figures that we need to put in, div R is 0, div F is 59. I've already got these preset to 90 megahertz, and div Q is 3. So whatever you want to set them to, you can do that. If you wanted a 100 megahertz clock, there we go, 66 and 3. 0, 66 and 3. And now we need to instantiate the Avalanche CPU. And we do that in a similar way. I'm not going to make you sit down and watch me type it all in, so again I'm going to copy and paste. The CPU is instantiated. We have a clock input which is coming from the PLL output, and then we have the 6 signals from the CPU. We've got data in, the read strobe, the read address, we have the write strobe, the write address and data out. Now the data in, AV data in, AV read and read address, in this case we're not going to be using them, but I've included them anyway so you can see how it should be connected. And the other thing we need to do is to create some registers and wires to actually connect these up. Again, copy and paste. So those are the essentials in for what we need, and now we need the actual logic, which is going to take the output of the CPU and route that through to our LED pin. And learn to spell. Always at the pos edge clock. Now what we want, in order to write to the output, we need to check that, make sure we only write when the write strobe is active. So now if the write strobe is active, we're going to be writing. Where do we write? Well, the address AV write comes out of the processor, so we need to take a look at that. And we only need to look at the lower 8 bits of the address. There's a 16-bit address coming out, but we only need to actually look at the lower 8 bits because the AV write strobe is already decoded the upper 8 bits, which must be 01 hex because that is the port range that the CPU outputs from. So the very fact that we're using AV write means that the port address is 01 something something, and that's the something something that we need to decode. So we're going to put that in a case statement. And it's going to be the AV write address. Okay. Which address? The address of our LED is 100 hex. So in this case we need to make sure that the lower 8 bits are 00. The 01 is already decoded, as I said, by AV write. And what we're going to do is say LED 4 is assigned AV data out bit 0. And bit 0, as we said, is our counter that we were incrementing in software. The lowest bit increments on every count, so that's what we're using to toggle our LED. And I think that is pretty much it. That's our high level output. Save that. Okay, we have our top level Verilog file, cpu.v, and we have our assembler source code. And the next thing to do is to assemble the source code and generate the files that's needed to build the project. Now, I've already done this while I wasn't recording and it failed. So I'm going to do it again and show you what happened. And it says label found outside of process. And if we have a look here, the Blinky label, we have an end process, but we don't have a process directive. Every process starts with a process and finishes with end process. And Blinky doesn't begin with a process. It hasn't got a name. And this is a cut and paste error. Happens to me all the time. So let's correct that. And it needs a name. I could call it P1, but it's the Blinky process. We'll call it Blinky. Okay, let's save that and give it another try. We're not doing so well, are we? In fact, it wasn't just the Blinky process that I missed, it was all the register definitions as well. So let's put those back in. Okay, we have the Blinky process, the registers that the process is going to be using, and then the code. Let's save that. Third time lucky? Yes. Now we need to synthesize and place and route our file, and we have a make file which will control all of that, so all we have to do is type make, and hopefully okay, we have more typos. Let's try that again. We have an unexpected end, and I forgot an end module. Okay, that succeeded. And if we have a look back up here, we've requested that the circuit works at 90 megahertz. In actual fact, it will run at 108.42 megahertz. So we're well within our 90 megahertz. And this is what I'm looking for. We're using 650 of our 7,680 logic cells. So a very, very small footprint. And now we can program that into the IceFun module with make burn. How about that? Our LED flashes.